You've probably heard that Voyager 2 left our solar system, but do you know what it actually saw out there? The answer isn't just a simple crossing from one region to another. It's a mind-bending discovery that reveals the edge of our solar system behaves more like a violent storm front than the calm boundary we expected. From twisted magnetic fields that defy predictions to mysterious particles that shouldn't exist, Voyager 2's journey into interstellar space uncovered secrets that are forcing scientists to completely rewrite the textbooks about where our cosmic neighborhood truly ends. In 1977, at the height of the Cold War, and just as humanity was beginning to understand the outer solar system, NASA launched two twin probes, Voyager 1 and Voyager 2. Their original mission was ambitious but modest compared to what they ultimately achieved. They were designed to take advantage of a rare planetary alignment, a cosmic window that would allow a single spacecraft to slingshot around Jupiter, Saturn, Uranus, and Neptune, visiting all four giant planets in one extended journey. Voyager 2 is still the only spacecraft ever to have visited Uranus and Neptune up close. But what no one fully realized at the time was that these two machines would outlive their original mission goals by decades. They would continue onward, powered by nuclear batteries, carrying instruments designed to measure magnetic fields, cosmic rays, and plasma particles far beyond the worlds they were sent to study. And in doing so, they would slowly begin the most important journey of all, the crossing from the solar system into interstellar space. For years, scientists debated exactly where the edge of the solar system lies. Many assumed it ended at Pluto, the icy dwarf planet, or at the Kuiper Belt, a region filled with comets and frozen bodies. But as Voyager 1 and Voyager 2 pressed outward, it became clear that the true boundary is something invisible, a frontier defined not by objects, but by forces. That boundary is called the heliopause. The heliopause is the place where the solar wind, a constant stream of charged particles, emitted by the sun, finally weakens to the point where it can no longer push back against the thin, but immense pressure of particles and fields that fill our galaxy. Inside the heliopause, we live in a bubble of solar influence, a protective shield that has surrounded Earth and the other planets since their birth. Outside, it lies interstellar space, a realm dominated not by the sun, but by the galaxy itself. Voyager 1 was the first to cross that boundary in 2012. But its plasma instrument had failed years earlier. This meant scientists could not measure directly how the density of plasma changed during its crossing. It was an extraordinary achievement, but it left many unanswered questions. Voyager 2, still carrying a working plasma detector, would become the crucial piece of the puzzle. In November 2018, Voyager 2 finally reached that invisible threshold. The spacecraft detected a dramatic drop in the solar wind and a sharp rise in cosmic rays originating from outside the solar system. Its plasma instrument recorded an unmistakable increase in density, the signature that it had passed through the heliopause and into interstellar space. This was more than just a scientific milestone. It was a human one. For the second time in history, a machine built by us on Earth had left the protective cocoon of our sun and entered the vast unknown between the stars. Voyager 2 now joins its twin as an eternal emissary, a silent traveler carrying the voices of Earth encoded on the golden record, greetings, music, and sounds meant for any distant intelligence that may one day discover it. The crossing of Voyager 2 is not only proof of our technological persistence, but also a profound symbol of our place in the universe. For billions of years, Earth and all life on it has existed inside the safety of the sun's sphere. But Voyager 2 shows us what lies beyond, and in doing so, it expands the borders of the human imagination itself. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. For centuries, humanity has wrestled with a deceptively simple question. Where does the solar system end? At first, the answer seemed obvious. Ancient astronomers defined it by the visible planet, from Mercury to Saturn, the wandering stars that moved differently from the fixed constellation. When telescopes revealed Uranus, Neptune, and eventually Pluto, it seemed the map was complete. For most of the 20th century, Pluto was considered the last stop, the frozen edge of our sun's domain. But Voyager 2's journey revealed that this picture was incomplete, even misleading. The solar system is not neatly bounded by the last planet or the farthest orbiting rock. Instead, its true border is invisible, sculpted not by planets, but by the forces of the sun itself. That force is the solar wind, a continuous outflow of charged particles streaming in all directions at nearly 1,000,000 miles per hour. The sun has blown this wind for billions of years, and over that time, it has inflated a giant bubble around itself. A bubble that contains every planet, every comet, every asteroid. Scientists call this bubble the heliosphere, and its outer skin, where the solar wind collides with the thin breath of the galaxy, is known as the heliopause. Unlike a planet's orbit, the heliopause isn't fixed. It shifts, expands, and contracts depending on solar activity. When the sun is active, bursting with flares and storms, the heliosphere swells outward. When the sun quiets, the heliosphere shrinks, allowing interstellar particles to creep closer in. This makes the boundary more like a breathing membrane than a solid wall. Voyager 2 was able to confirm this reality with direct measurement. As it approached the heliopause in late 2018, its instruments recorded a sharp decline in the number of solar particles, the fast-moving protons and electrons that normally dominate inside the heliosphere. At the same time, detectors picked up a dramatic increase in high-energy cosmic rays from beyond the sun's influence. This was the signature scientists had been waiting for, the unmistakable fingerprint of crossing into interstellar space. Unlike Voyager 1, which lacked a working plasma instrument during its own crossing, Voyager 2 provided the first direct confirmation of the density shift at the boundary. The data showed that just outside the heliopause, the plasma was far denser than within, proving beyond doubt that the spacecraft had pierced the true edge of the sun's domain. This discovery forced scientists to redraw the map of our cosmic neighborhood. The edge of the solar system is no longer Pluto, no longer the Kuiper Belt. It is this dynamic frontier, an invisible border that surrounds everything we know. And there's something profound in that. For the first time, we realize that our home star carries its own protective shield, a bubble that wraps around its planets and worlds, much like an atmosphere shields Earth itself. Beyond that shield lies a very different environment, one not shaped by our sun, but by the galaxy. Voyager 2 showed us that the edge of the solar system is not a place, but a process, a balance point between two vast forces, the push of the sun's wind and the pressure of interstellar space. And in crossing it, the spacecraft has given us not just new science, but a deeper understanding of where home truly ends. When scientists first imagined the heliopause, the invisible boundary between the solar system and interstellar space, many pictured a smooth, almost mathematical surface, a clean transition where the solar wind would simply stop and the galaxy's influence would begin. Voyager 2 shattered that image. What it found was not a calm border but a chaotic frontier, more like the crashing surf at an ocean's shoreline than a glassy, still pond. Instead of a single, sharp dividing line, Voyager 2 revealed layer upon layer of turbulence, irregular regions where plasma densities shifted unexpectedly, and magnetic fields twisted and bent in unpredictable ways. The spacecraft's plasma detector recorded sudden fluctuations, not a steady climb or drop. One moment, the data suggested Voyager was still within the influence of the sun. Then moments later it appeared to be fully immersed in galactic space. This back-and-forth pattern painted a picture of a messy, storm-driven boundary, a transitional zone full of eddies, swirls, and currents. Imagine standing at the shoreline of an ocean during a storm. Waves crash into each other, foam mixes with water, and debris is swept back and forth. That is what the edge of our solar system looks like. Not neat, not tidy, but a place of constant motion and violent interaction between the solar wind and the interstellar medium. One of the most surprising findings was the way magnetic fields behaved in this region. Instead of aligning smoothly, the solar magnetic field appeared to twist into knots and mingle with the galactic field beyond. It was as though the sun's protective bubble was fraying, its outer fabric torn and tugged by the greater magnetic forces of the Milky Way. These discoveries challenged long-held models. For decades, simulations suggested a relatively stable heliopause. But Voyager 2's measurements forced scientists to admit that reality is far messier. The heliopause is not a static border at all. It is a dynamic, turbulent frontier shaped by competing cosmic pressures. This turbulence matters. The way energy, plasma, and magnetic fields interact at this frontier may determine how much galactic radiation seeps into our solar system, influencing the space environment around Earth and other planets. It is not just a boundary out there. It is a shield whose strength and stability affect everything inside it. Voyager 2 revealed that the edge of the solar system is alive with activity, a cosmic storm zone where the sun's influence and the galaxy's pressure endlessly collide. Far from being a smooth transition, it is a boundary that breathes, churns, and shifts, reminding us that even at the outermost limits of our home, the universe is in constant motion. Voyager 2's journey revealed a truth that challenged centuries of assumptions. The heliopause is not an impermeable wall. Instead, it behaves more like a sieve, allowing particles to flow both ways. Interstellar material seeps into the heliosphere, while solar particles escape outward, drifting into the vastness of interstellar space. Inside the heliosphere, we've always assumed a certain level of protection. The solar wind, combined with the sun's magnetic field, was thought to form a shield that largely kept the chaotic energy of the galaxy at bay. But Voyager 2's measurements show that this shield is not as secure as we imagined. Cosmic rays and energetic particles from outside can penetrate the sun's domain more easily, occasionally making their way toward Earth and the other planets. This leaky nature has profound implications. The inflow of galactic particles can subtly alter planetary environments over long periods. On Earth, for instance, fluctuations in cosmic rays may influence cloud formation, atmospheric chemistry, and even rates of genetic mutation. Over geological timescales, these subtle influences could have shaped the evolution of life, contributing to mass extinctions or evolutionary leaps. Conversely, solar particles are not confined to the heliosphere either. Voyager 2 observed streams of solar material escaping into interstellar space, merging with the galactic medium in ways scientists had not anticipated. This exchange suggests that our solar system is not an isolated bubble drifting alone in the galaxy. It is connected, porous, and in constant interaction with its surrounding. These findings also challenge how we think about other star systems. If our sun's heliosphere is leaky, what does that imply for exoplanets orbiting distant stars? The boundaries of their stellar bubbles may be just as dynamic, potentially exposing those worlds to interstellar weather that could influence habitability. Voyager 2's observations revealed that the edge of the solar system is not a rigid frontier, but a living interface, a boundary that breathes, pulses, and flows. This discovery forces us to rethink how solar systems interact with the galaxy at large, and underscores the interconnected nature of our cosmic neighborhood. Ultimately, the leaky heliopause tells us that Earth's environment, while seemingly stable and protected, is in fact subtly influenced by forces far beyond the Sun. Voyager 2 has illuminated the reality that our planet is not isolated, but part of a vast, dynamic galactic web. A humbling reminder of how intimately connected we are to the broader universe. As Voyager 2 ventured beyond the heliopause, one of its most revealing instruments came to the forefront: the plasma wave sensor. This device, designed to detect the density and movement of charged particles in space, became the key to understanding the true nature of interstellar space. The readings were dramatic. As the spacecraft crossed the heliopause, the plasma density suddenly spiked, far higher than anything measured within the Sun's influence. This sharp rise confirmed what other instruments had suggested. Voyager 2 had indeed entered interstellar space, leaving the protective bubble of our solar system behind. It was a historic moment, marking humanity's second direct encounter with the space between the stars. Yet the story was far more complex than a simple increase in density. The plasma waves showed unexpected fluctuations, sudden spikes and dips that hinted at a turbulent environment. These variations were not random. They indicated the presence of shock waves and mixing zones at the boundary, created by the interaction of the Sun's dying solar wind with the vast pressures and currents of interstellar space. Imagine a river flowing into the ocean. The moment freshwater meets saltwater, currents twist and churn, creating eddies and whirlpools. Voyager 2 was observing a similar cosmic phenomenon, a cosmic mixing zone, where solar and galactic forces collided in a dance of energy and motion. Some of these fluctuations were caused by the Sun itself. Solar eruptions, bursts of energy, plasma, and magnetic fields ripple outward through the heliosphere, sometimes reaching the very edge and impacting the boundary in dramatic ways. At the same time, galactic forces, including distant shock waves from supernovae and interstellar turbulence, pressed inward, colliding with the Sun's outflow and creating additional disturbances. This interplay of forces revealed that interstellar space is far from uniform or still. Instead, it is dynamic and unpredictable, a turbulent ocean of charged particles, waves, and magnetic eddies. Voyager 2's plasma measurements were the first direct evidence of this activity, showing scientists that the edge of the solar system is alive with motion, constantly reshaped by both local and galactic events. The significance of these plasma wave discoveries extends beyond pure physics. Understanding the density and dynamics of interstellar plasma is crucial for predicting the flow of cosmic rays into the solar system, for modeling space weather, and even for planning future interstellar missions. It gives us a glimpse into the invisible forces that shape the environment of Earth and the planets, and allows scientists to probe the mechanics of the galaxy itself. Voyager 2's plasma wave finding transformed our view of space beyond the Sun. What was once thought to be a quiet frontier is actually a churning, energetic realm, a place where the solar wind fades but leaves behind echoes of its influence, mixing with the vast and mysterious currents of the Milky Way. Each fluctuation, each spike in plasma density, is a message from the galaxy itself. And Voyager 2 is the first human-made interpreter of these interstellar signals. As Voyager 2 drifted deeper into interstellar space, its magnetometer began revealing some of the most astonishing and unexpected findings of the mission. Scientists had long predicted that the Sun's magnetic field would fade gradually at the heliopause, giving way to the relatively uniform magnetic field of the galaxy. What Voyager 2 found, however, was far more complex. The interstellar magnetic field beyond the heliopause was oriented nearly perpendicular to what models had predicted. This meant that the Sun's influence did not simply vanish or blend smoothly into galactic space. Instead, the Sun's magnetic threads appeared to twist, coil, and intertwine with the larger galactic field, forming a tangled, unpredictable structure. Imagine a river meeting a vast, swirling ocean. The freshwater currents do not simply stop, they twist, spiral, and mix with the larger body, forming vortices and eddies. This is essentially what Voyager 2 observed at the edge of the solar system. The Sun's magnetic fingerprint persists beyond the heliopause, entwining with galactic forces in ways that defy simple explanations. These findings challenged decades of assumptions about how stars interact with their galactic environment. Instead of isolated solar bubbles floating alone, Voyager 2 revealed that stellar magnetic fields are deeply connected to the galaxy itself, forming a network of influence that stretches far beyond the reach of planets. The twisting magnetic field suggests that our heliosphere is not a closed, insulated bubble, but part of a much more dynamic cosmic fabric. the implications for space science are profound. Magnetic fields guide charged particles, shape the flow of cosmic rays, and influence the movement of interstellar plasma. Understanding their orientation and behavior is critical for predicting the exposure of Earth and other planets to high-energy radiation. Voyager 2's data show that this exposure is far more complex and variable than previously thought, shaped by a tangled interplay of solar and galactic forces. Even more intriguing, these magnetic twists may reveal clues about ancient galactic events. Shock waves from distant supernovae, the influence of nearby stellar winds, and the motion of interstellar clouds could all contribute to the magnetic turbulence Voyager 2 observed. Each fluctuation in the field is like a fingerprint left behind by cosmic processes that span millions of years. Voyager 2's magnetometer. Readings have fundamentally reshaped our understanding of the solar system's frontier. The edge is not a simple line, but a living interface, where the sun's influence and the galaxy's magnetic energy meet, collide, and merge. It is a place of dynamic tension, where invisible forces shape the very structure of space itself. For the first time, humanity could see the sun not as an isolated star with a neat bubble of protection, but as part of a vast, interconnected galactic network. Voyager 2 revealed that our solar system is embedded in a magnetic web, influenced by both local and distant cosmic forces, a discovery that has profound implications for understanding the galaxy, the heliosphere, and the very environment that surrounds our planet. As Voyager 2 ventured further into interstellar space, it began encountering phenomena that defied expectation. Among the most startling discoveries were high-energy particles that could not be traced back to the sun or typical galactic cosmic rays. These particles were exotic, anomalous, and utterly mysterious, suggesting processes at work in the galaxy that scientists had never observed directly before. The spacecraft's instruments recorded bursts and spikes of energy, fluctuating in both intensity and composition. These particles were unlike anything measured within the heliosphere, hinting at the presence of hidden astrophysical mechanisms, possibly remnants of ancient supernovae, colliding stellar winds, or even massive, unseen structures lurking within the local interstellar medium. Each anomaly was like a whisper from the galaxy's turbulent past, a signature of events that occurred millions of years before the sun even formed. Voyager 2's data also revealed what scientists are calling cosmic weather, variations in particle flows, plasma densities, and magnetic field orientations that resemble storms or currents in an invisible interstellar ocean. Just as weather on Earth results from the interaction of air, temperature, and pressure, these cosmic fluctuations appear to arise from interactions between the sun's fading influence and the dynamic galactic environment. Some of these variations may be shaped by shock waves from distant supernova explosions, sweeping across interstellar space like invisible tidal waves. Others could be caused by dense clouds of interstellar gas or by the twisting and folding of magnetic fields. The result is a turbulent, ever-changing environment where the flow of energy, particles, and plasma is never uniform. The discovery of these mysterious particles forces scientists to reconsider assumptions about the interstellar medium. No longer can it be thought of as a quiet, uniform void. It is instead a complex, dynamic region full of activity and hidden structure. Voyager 2 has shown that the space between stars is alive with subtle motion, violent bursts, and energy flows that are only beginning to be understood. These findings also have implications closer to home. The behavior of cosmic rays and energetic particles at the heliopause can influence the radiation environment throughout the solar system, subtly affecting planetary atmospheres, magnetospheres, and potentially even biological processes on Earth over long time scales. Voyager 2 is revealing that our planet's environment is not entirely shielded from the broader galactic forces. It is subject to the moods and tempests of cosmic weather. Perhaps most tantalizing is the possibility that these particles may be evidence of new astrophysical phenomena. Could they point to exotic processes we have yet to identify? Might they originate from ancient stellar remnants, unseen gravitational giants, or other phenomena lurking in the local bubble of the Milky Way? Voyager 2 is providing the first hints, and scientists are only beginning to decode their significance. Through these mysterious particles and the patterns of cosmic weather they trace, Voyager 2 is teaching humanity a profound lesson. Interstellar space is not empty. It is a living, breathing environment full of energy, turbulence, and stories from the distant past. Each signal the spacecraft sends back is a clue, a fragment of a much larger narrative about the galaxy we inhabit. Beyond the heliopause, Voyager 2 began capturing something extraordinary: persistent oscillations in the interstellar plasma. These subtle vibrations, imperceptible to human senses, are effectively the sounds of interstellar space, faint echoes of activity that have traveled across vast stretches of the galaxy to reach the spacecraft. These plasma oscillations are not random. They suggest the presence of massive, slow-moving waves and disturbances, the lingering fingerprints of titanic cosmic events such as ancient supernovae, colliding stellar winds, or the motions of dense interstellar clouds. Each oscillation carries information about the forces that shape the local interstellar medium, revealing a dynamic environment that is far more active than previously imagined. Imagine a vast cosmic ocean. Even in regions where no star shines, subtle waves ripple across the invisible medium, carrying the energy of events that occurred millions of years ago. Voyager 2 is listening to this silent symphony, recording a hidden soundtrack of the galaxy for the first time in human history. The spacecraft's plasma wave instrument allowed scientists to measure the frequency and intensity of these oscillations, offering unprecedented insight into the structure and composition of interstellar space. These subtle signals reveal that the medium is not a uniform void, but is instead structured, active, and responsive to forces both near and far. What makes these discoveries even more remarkable is their implication for our understanding of cosmic connectivity. The oscillations hint that interstellar space retains memory. The echoes of past events persist, influencing the movement of particles, magnetic fields, and even cosmic rays across light years. Space is not silent or inert. It is a dynamic environment where energy travels, interacts, and evolves over vast distances. For humanity, this means that our solar system is embedded in a universe that is alive with hidden motion. The Sun's protective bubble is just one player in a larger interstellar orchestra, and Voyager 2 has become our first instrument capable of hearing this cosmic music. Each plasma oscillation is a clue, a message from events long past, reminding us that the galaxy is a living, ever-changing environment. These faint interstellar sounds also help scientists refine models of space weather, cosmic ray propagation, and the behavior of magnetic fields beyond the solar system. By studying the plasma oscillation, researchers can trace the influence of distant supernova, map turbulent interstellar clouds, and understand how energy travels through the galaxy. Voyager 2 has revealed that interstellar space is far from silent. It vibrates, pulses, and resonates with echoes of ancient cosmic drama. For the first time, humanity has begun to listen to the universe itself, uncovering a hidden layer of reality that challenges our notions of emptiness and quiet. Through these observations, Voyager 2 reminds us that the universe is not a passive backdrop. It is alive with structure, motion, and memory, and by tuning into these subtle interstellar sounds, we gain a new understanding of our place in a vibrant and dynamic galaxy. Voyager 2's journey into interstellar space has profound implications, not just for our understanding of physics and astrophysics, but for the very conditions that shape life on Earth. By studying the heliopause and the surrounding interstellar medium, scientists have realized that the solar system is more exposed to galactic forces than previously believed. Cosmic rays, interstellar particles, and magnetic turbulence do not stop at the sun's edge. They seep through, interacting with planetary environments in subtle but potentially significant ways. On Earth, these high-energy particles can influence atmospheric chemistry, cloud formation, and even climate patterns over geological timescales. Changes in the local interstellar environment, such as shock waves from distant supernova or the passage through denser interstellar clouds, could alter the influx of cosmic rays, occasionally intensifying radiation at Earth's surface. Over millions of years, such variations may have contributed to evolutionary pressures, potentially even influencing mass extinctions or bursts of genetic mutation that shaped the path of life. The implications extend far beyond our solar system. If the edge of the Sun's heliosphere is turbulent, porous, and dynamic, then the stellar bubbles of other stars, their astrospheres, are likely equally complex. Exoplanets orbiting distant stars may face cosmic environments far more hostile or variable than previously imagined. The habitability of alien worlds could be shaped not only by their distance from their star, but also by the structure and stability of their star's magnetic bubble, the density of surrounding interstellar clouds, and the intensity of galactic cosmic weather. Voyager 2's findings are prompting scientists to rethink the criteria for habitability. Life may require not just the right temperature or the presence of water, but also a protective stellar shield that mitigates cosmic radiation and interstellar influences. By comparing the Sun's heliosphere to other stellar bubbles, researchers can better understand which planetary systems are more likely to sustain life, and which may be exposed to intense cosmic forces. These discoveries also have implications for long-term planetary evolution. Variations in cosmic ray flux could affect atmospheric erosion, chemical reactions, and even the formation of organic molecules essential to life. The realization that the universe is dynamic, turbulent, and interconnected underscores that life on any planet is influenced not only by its star, but by the broader galactic environment. Ultimately, Voyager 2 shows that Earth is not isolated in a tranquil bubble of safety. Our planet exists within a cosmic ecosystem, influenced by interstellar forces, shaped by galactic currents, and subject to the rhythms of the Milky Way. This perspective transforms how we understand both our solar system and the potential for life beyond it. Through its ongoing journey, Voyager 2 invites us to reconsider the delicate balance that allows life to thrive, while highlighting the profound complexity of the galaxy. Its data serve as a reminder that the story of habitability is not just about planets and stars, but about the entire interstellar environment that envelops them, connecting each system to the wider cosmos in ways we are only beginning to understand. Voyager 2's journey into interstellar space represents one of humanity's most profound scientific and philosophical achievements. Launched over 4 decades ago, the spacecraft continues to send back invaluable data, reshaping our understanding of the solar system's boundaries, the galactic environment, and the very nature of interstellar space itself. Its findings have already transformed models of heliospheres, revealing them not as isolated static bubbles but as dynamic, permeable structures constantly interacting with the galaxy. By studying the tangled magnetic fields, plasma oscillations, and cosmic rays at the edge of our solar system, Voyager 2 has provided insights that extend far beyond our own neighborhood. Scientists are now applying these lessons to astrospheres around other stars, helping to assess the protective shields surrounding exoplanets and the potential for life elsewhere in the galaxy. The spacecraft has turned abstract theoretical concepts into empirical data, offering a first-hand glimpse of how stars and their planetary systems are interconnected with the broader galactic environment. Voyager 2's discoveries are also guiding the next generation of space exploration. Engineers and scientists are already designing new probes, equipped with advanced instruments, faster propulsion, and enhanced communication systems to continue humanity's journey into interstellar space. These future explorers will venture further, faster, and more intelligently than Voyager 2, building on the path it has charted. Yet none will experience the same thrill of first contact, the awe of being the first human-made object to cross into the uncharted void beyond the Sun's influence. Beyond science and engineering, Voyager 2's mission carries profound philosophical significance. It reminds us that the universe is interconnected, unpredictable, and full of hidden mysteries. The probe's discoveries, from turbulent magnetic fields to mysterious particles and interstellar sounds, reveal a cosmos that is far more complex than early models predicted. Our solar system is not an isolated island. It is part of a living, dynamic galaxy, influenced by forces that ripple across light years. Voyager 2 also stands as a testament to human curiosity, ingenuity, and perseverance. Even decades after launch, the spacecraft continues to function in a harsh, unforgiving environment, its faint signals traveling billions of kilometers to reach Earth. Each data packet represents the dedication of thousands of scientists and engineers, as well as the enduring human desire to explore, understand, and connect with the cosmos. The probe's legacy is twofold. Scientifically, it has expanded our knowledge of the heliosphere, interstellar medium, cosmic rays, and galactic interactions, opening new avenues of research and inspiring missions that will follow in its wake. Culturally and philosophically, it serves as a symbol of exploration, reminding humanity that even at the edge of the unknown, courage and curiosity can push the boundaries of understanding. As Voyager 2 continues its lonely journey into the interstellar expanse, its story encourages us to look outward, question assumptions, and embrace the unknown. Every new reading, every unexpected anomaly, every faint whisper from beyond the sun's protective bubble is an invitation to future generations to explore further, to seek deeper, and to continue the quest that began with a small spacecraft launched from Earth nearly half a century ago. In the end, Voyager 2 teaches us that the edge of the solar system is not an ending. It is a beginning, a doorway to infinite discovery, a living testament to humanity's unyielding spirit. Its legacy will endure for generations, guiding our understanding of the galaxy, inspiring new missions, and reminding us that the universe, in all its complexity and mystery, is waiting to be explored. Voyager 2's Adi towards 2's voyage into interstellar space is far more than a tale of engineering triumph or scientific discovery. It is a story of human curiosity reaching beyond the known, a reminder that even the most distant and hostile corners of the cosmos are within our reach when ingenuity and perseverance guide us. As it drifts ever farther into the galaxy, Voyager 2 carries with it the legacy of Earth, our questions, our ambition, and our desire to understand the universe. Each faint signal it transmits back is a message from the frontier, a whisper from the edge of the solar system telling us that exploration has no true end, only new horizons. The revelations of turbulent heliospheres, mysterious cosmic particles, and interstellar oscillations challenge our assumptions, reshape our models, and inspire a deeper appreciation for the complexity and interconnectedness of the galaxy. The universe is not static. It is alive with energy, motion, and hidden forces. And Voyager 2 is our first emissary, charting this vast, dynamic realm. For scientists, explorers, and dreamers alike, Voyager 2's journey is a call to continue the quest for knowledge. Future missions will push farther, faster, and more precisely, but they will always follow the path first illuminated by this small, resilient spacecraft. It is a testament to the power of curiosity, the courage to venture into the unknown, and the boundless human spirit that seeks to understand its place in the cosmos. And so, the story of Voyager 2 reminds us that the edge of the solar system is not a limit, but a beginning, a doorway to the infinite, where the mysteries of interstellar space beckon, waiting for the next generation to listen, explore, and discover. The universe continues its silent dance, and Voyager 2 continues its lonely, tireless journey, carrying humanity's voice into the stars, a beacon of hope, wonder, and the enduring drive to know what lies beyond. The voyage is far from over. The adventure has just begun. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries. Because some secrets are just waiting to be uncovered.